Welcome to this seventh lecture video for Physics 4A. This is the first of two sets of lecture videos in which we will showcase examples of solving force analysis problems with the four-step process that we call standard strategy. There are more questions and more types of questions that can be solved by the application of standard strategy than we can list in these two sets of lecture videos. So I encourage you to try other problems on your own and look for additional examples that have been provided elsewhere in the course. Examples that are included in this lecture video set are paradigmatic examples, but these are by no means comprehensive. For this set, we will warm up with an example of free body diagram drawing exercise, highlighting in particular the Newton's third law check, which is important in questions dealing with multiple interacting bodies. Then we will show three examples of applications of standard strategy in an approximate order of increasing difficulty. That is, the first two examples cover scenarios that a smart student may be able to answer intuitively. In the third example is where some form of organized, systematic problem solving begins to become necessary, and the systematic approach we teach and recommend is standard strategy. The next example you will see is perhaps the most textbook example of a force analysis problem-solving approach, dealing with an object on an inclined plane. And we will include a friction force as well to better illustrate the usefulness of standard strategy. Finally, the last example, involving two bodies interacting through a tension force, is where you will begin to see an intuitive approach struggle. Even for very smart students who can keep track of multiple ideas and calculations in their head, and where a systematic step-by-step approach such as a standard strategy shine through. In applying standard strategy, you will always know what the next step in the problem-solving approach is, no matter how complicated the situation. And it is only in applying a multi-block strategy, like standard strategy, that you can calculate the tension force between two interacting bodies, as in this example. We will cover additional, more complicated examples in the next set of lecture videos, and we will also include the circular motion in our coverage then. My goal in this demonstration right now is to kind of show you what to watch out for, so that you have more confidence as you are working through these, that when you have drawn all the forces, that you have drawn all the forces, and if there's something missing, then then you have the tools to spot whatever it is you may have missed the first time around. So let me look at the question to make sure I understand the friction. So it says, yes, there's a static friction between the blocks, and this surface is frictionless. So I'll have that information in mind as I draw the free body diagram. So when we draw free body diagram, our recommendation is to draw two separate diagrams. I know sometimes there are different conventions. There are textbook authors who will just draw arrows on this and maybe even use the surface as a place to attach the force vectors to. I've seen that, and I can see some justification for it, so that you are thinking about where the force is coming from. And if you are following that alternate convention, I will recognize it and not mark you as wrong just because you're doing things a little bit differently. Having said all that, that really isn't what I recommend, because I think, especially at this stage, there's more value in drawing a clean, clear free body diagram that whose purpose really is to help you go through the standard strategy. So for that purpose, really what's useful are the simplest possible free body diagrams. So to make the diagrams as simple as possible, you should really draw one dot for one of the objects and a 2-second entirely separate dot for the second object. And when I draw them, I almost deliberately don't geometrically arrange them in the way they are in the physical space, because they are two separate diagrams. They don't necessarily have anything to do with each other. Yeah. So with that, let me start drawing forces. Whenever the question tells me that there's a force on something, I like to draw it because it's nice to be told what to expect, and I should have kind of used that information. So I have F, apply the force. That's going to be on block M1 at this angle here. So let me just draw that. And if you want, you can draw some hints on the angles that are given and this sort of thing, just to make sure that you can clearly see what are the force vectors and which are not. Okay, I've drawn the applied force, and I'm asking myself this question: did I draw all the forces? And as you're asking the question, one of the easiest thing to get is gravity. Most of our scenarios deal with while you are near the surface of the Earth, so there's always going to be gravity. So let me draw that gravity that's always there. It's for me, it's mostly useful as a starting place, because it's really hard to stare at an empty page and keep asking yourself, did I draw all the forces? And often the answer is, I don't know, it's empty. I have no idea if that looks consistent with the real world. And once you've drawn some arrows as a starting place, then you can ask this question: are the pictures you have drawn consistent with the reality? As in, the force vectors I've drawn here tells me that my acceleration is pointed that way. Does my intuition about this setup agree with this supposed direction of acceleration? And I hope your answer is no, because as you're looking at it, you can kind of guess intuitively that any acceleration has to be rightward. So that tells me that there must be some vertical force on M1 that's that's stopping it from accelerating downward. And there is, and that should be the normal force from this surface of contact. You have the surface contact between M1 and M2, so there must be a normal force that's pushing it up. And I have a sense that I'm going to get a lot of normal forces, so let me label this N1. And, oh, wait, sorry, 1 second, I forgot G here. I mean, it's something that I'm going to remember as I'm writing down Newton's second law equation, but might as well fix it now. So as I'm staring at this free body diagram, if I'm and I guess I might as well also draw normal force on M2, because I do kind of know M2 cannot be accelerating downward. That doesn't make sense. So I see, oh, there is a surface of contact here. So there must be a normal force from that on M2. So let me draw that as well. M2. And again, I ask myself this question: did I draw all the forces? And with the mass M1, if your answer at this point is yes, that might be okay for now. I'll come back to that. But I hope as you are looking at the free body diagram for M2 that something looks wrong to you, that it looks like you are missing some force. Because the question said the friction force here is a static friction force. And what that means is that there's no relative motion between M1 and M2. So if M1 is accelerating to the right, M2 must be accelerating to the right with the same acceleration, so that they are moving together. So as you're looking at that, and I don't have any rightward forces, I must be getting it somewhere. And the first time you face a scenario like this, it might take you some time. Totally fine. Spend the time. Make sure you are not drawing this force on M2, because it's not acting on M2, it's acting on M1. So don't draw that force on M2. The only thing that could have possibly pushing M2 to the right of the two things that are touching it, the surface below and the surface above, is really the surface above, one that has static friction force. So there's a static friction force on M2, and you need to draw it. A static friction force that's pushing M2 to the right. That's where its acceleration comes from. Now, as you're looking at these two diagrams and you're asking yourself, did I draw all the forces? And if it looks like you have, I don't blame you. It kind of looks complete, you know. Here I can get rightward acceleration. Here I can get rightward acceleration. So what am I missing? And this is where I am telling you about this thing that I think that was in the lecture, what I like to call Newton's third law check. So Newton's third law is the law of interaction that says when object A pushes on object B, then object B pushes back on object A. So what I mean by Newton's third law check is you need to look at every single one of the forces on your diagram, and you need to be able to answer this question. These two set of questions. First question, is it an internal or external force? As in, is it a force that's exerted on the body from some other object outside your system? That would be the external force. And if the answer is yes there, then you're done. With the external forces, there's nothing more you need to do. If it's an internal force, then you need a second follow-up question. Where is your reaction force pair? So that's the check that I need to go through. I have 6 forces here, so let me just go through them one by one. I have gravity. I'm asking, is it an internal or external force? Well, where does gravity come from? It's coming from Earth. It's the Earth pulling it. Earth is not... my system is this, mass M1 and mass M2. That's my system. So Earth isn't part of it, so it's an external force, I'm done. I had this applied force. Is it an internal or external force? Well, it's some outside agent that's doing whatever the problem says it's doing. So it's an external force, whatever that outside agent is. We're not drawing his, her, it for everybody diagram. So that's an external force, no reaction force needed. Now I'm looking at this N1, looking at this normal force and asking, where is this normal force coming from? It's coming from this surface of contact. So it's M2 pushing M1. So I need to have a reaction force pair on M2. And I don't see that. So that's what I forgot I need to draw that. So there's a reaction force pair. And as I'm drawing the reaction force pair, I like to label it with the same label as my action force, because that's really the main information you get out of Newton's third law. That's Newton's third law says, well, it says these are two in opposite directions and that they have the same magnitude. And since they have the same magnitude, I can just use the same label. Don't need to switch it up. So yeah, that's one action reaction force pair. Or you could have actually swapped them, but I think most people get this N1 before you get this N1. So let's keep going. I have 3 more forces I need to check. So this force, if I check it again, then that's my reaction force pair. So they are paired up. We are good. This gravity, external force, I don't need to worry about it. And this friction force. So the friction force is coming from this surface of contact. So what's pushing M2 to the right? Must be M1. That's the object that's touching it, that surface that's providing friction force. So I need to have a reaction force pair to this friction force on M1. And I don't see that, so let me just draw that. And I hope as you're drawing this answers to some question that you might have had. Question of what difference does M2 make in the motion of M1? Because I think intuitively you would feel that as you are pushing M1, if M2 needs to move as well, then the presence of M2 matters. But up until I drew this friction force, nothing in this diagram depended on M2. And once you draw this friction force, then you see that's how these two objects interact. That's how M2 affects how quickly M1 can accelerate through this force of interaction between them. And all of this, so it's this is kind of the remarkable thing about standard strategy. You don't have to kind of reason through this interaction thing like in vacuum. If you don't have to insert it as some ad hoc thing. It just comes naturally into it out of Newton's laws that you are going through. Last and two, oh, that's normal force from this table surface, and table is outside object, so this is an external force, no reaction force pair needed. So we had these two action reaction force pairs, this set of normal force and this set of friction force. And with that, now this is a complete free body diagram. The forces drawn, kind of, you can arrange them in a way that it gives you the acceleration you intuitively know you should have. And I've done this Newton's third law check, so I know I haven't drawn any action force that's missing its reaction force pair that should be part of the diagram. So yeah, and it's in a situations like this when if I forget to do the Newton's third law check, I have actually forgotten some of these forces in a more complicated setup before. So I do strongly recommend that you get into habit of doing this whenever you are dealing with a multi-body system. Whenever your system has more than one object, then make sure you go through this check. And there are more complicated scenarios where once you start involving strings and pulleys. So when you see those scenarios, practice. In this and next couple videos, I want to illustrate the standard strategy. The standard strategy is an example, a paradigm of how we approach problem solving in physics. And what it exemplifies is how we take a given situation, break it down, apply laws of physics as we know them, in order to get an equation, which we then use to solve the problem. So let me first lay out the strategy. This applies specifically for forces problems. You draw a free body diagram, which is the graphical tool we use in force problems to lay out all the information we have so that we don't forget anything and we approach the problem systematically. And part of that systematic approach is we define a coordinate axis. And there are some guidelines to follow in how we draw that axis. We'll go over that. And once you have the coordinate axis defined, those axes were defined for a purpose. It's so that we can break forces down into components. And all these steps are really leading up to the final step in the strategy, which is the Newton's second law equation. And usually when you get to this point, you haven't finished solving the problem. What you have done is you have set up an equation which then can be algebraically solved for whatever the question is. So there's some mathematical steps to be done. All right, let's apply this strategy to this question on the screen. This is one of your homework questions. And it's a relatively simple question, so we'll actually be doing it the long way by applying the standard strategy. But I want you to illustrate it in this context first. So let's start with the first step. The first step is to draw a free body diagram. And the purpose of the free body diagram is to lay out all the information that's given so that we can be sure we didn't forget anything, and leave us with a graphic which shows all the information given in the problem in one glance. This is the most important step. If we identify the wrong force somehow, or if we forget to identify a force, then the rest of our steps will be wrong. So even though it looks like just drawing a picture, it is the most important step in the standard strategy. So let's identify all the forces. there are some easy ones. The problem gave us two forces. One applied force of magnitude F, and another applied force of the same magnitude but applied at an angle 30 degrees. And the problem doesn't explicitly give these other forces, and for this question you can actually ignore them too. But let's draw them for the sake of illustrating the strategy. So on this block there will be a gravitational force, which we'll call weight, and it'll end up being equal to mass times gravitational acceleration. And as drawn here, it looks like the block should be accelerating downward, and we know it doesn't. So there must be another force that we haven't identified yet, and that's the normal force. Alright, so as drawn here, it looks like the block should be accelerating to the right, and that is right. The question is asking for the resulting acceleration of the block. Alright, so what direction do you think this block will accelerate? It seems like a silly question because in this particular question it's rather obvious. It'll be accelerating to the right. But I ask that question anyway because this is important information for the next step, defining the axis. Whenever possible, we want to define the axis so that one of the axes is along the direction of acceleration. It's not a requirement, but it will make our future steps much simpler and more convenient. You will see soon. So let me define the axis so that the x-axis is along the direction of acceleration. Then the y-axis is perpendicular to that, and in this case happens to be along the normal force and gravity. Alright, the next step is to break forces into components. Fortunately, three of our forces are already along x or y axis. That would be one of the applied forces, the normal force, and the gravity. They are all already along x or y direction. The reason we break forces into components is to prepare for the next step, step number 4, where the Newton's second law equation gets written each time for each direction, once for x direction and once for y direction. This is consistent with the mathematical behavior of vectors, the independence of x and y directions. So we have one force that needs to be broken into components, and that's this other applied force F. And let me do that here. We have the y component and the x component. And while we are doing that, we want to come up with their expression too. So this theta is the 30-degree angle that's shown there. So we should that the y component should be f sine theta. We use SOHCAHTOA. This side here is the side opposite to the angle, so it's associated with sine. And the x component here is f cosine theta. Sort of what you would have expected. You could have guessed this, but next week you will see the situations where if you automatically associate x with the cosine and y the sine, that you will be sometimes wrong. So you want to get into the habit of always drawing these triangles. Alright, so that's step number 3. So all these steps 1 through 3 are really leading up to the final step, step number 4. Once you have correctly drawn the free body diagram and marked it up and labeled it correctly following steps 2 and 3, then all you need to do is in step number 4 is simply read off the information from this well-drawn diagram. So let me do that. So we are writing down Newton's second law equation, and what you should always remember about these vector equations is that they are really 2 or 3 if you are in 3 dimensions, 2 equations disguised as 1, because what it really means is that the x component of the net force is equal to mass times the x component of acceleration and that the y component of net force is equal to mass times the y component of acceleration. And this is where you will see why we chose acceleration to point only along the x direction with no component in the y direction. This way, we can say that the net force in the y direction adds up to 0. This isn't always possible, but whenever you can set up your equations this way, this simplifies your work a lot. And this is what the problem hint is getting at if you need to look at forces along both components. If you don't want to do all this extra work, you could just look at the forces along the x direction, and that would give you the answer you're looking for. All right, let's finish step number 4. So the net force in the x direction, that would be one of the applied forces, the whole thing, and the x component of the second applied force. And I guess that's it. Both the normal force and gravity are not along the x direction at all. So F plus F cosine theta is equal to mass times, and here it is the whole acceleration because the whole acceleration is along the x direction. So that's our first equation. And we do have second equation that we can write down. For this question, it doesn't give us any information that we are looking for, but let me write it down anyway for the sake of completeness. So the net force along the y direction involves the normal force, the gravity, and the y component of one of the applied forces. So saying that the normal force is in the positive direction, minus mg, and I guess y component of F is also downward. So minus F sine theta. And by the choice of our axis, this is equal to 0. So this is the end of the standard strategy. And note that it doesn't quite finish solving the problem for you. What it does leave you with is a system of equations. So I have two equations. If I only have two unknowns, then this is solvable. Let's count the unknowns. Force is known, theta is known, mass is known. What is not known is the acceleration. Let me use capital M consistently. Alright, so that's one equation, one unknown. And in the second equation, everything is known except for the normal force. So if the question were to ask you for the normal force, then we would have needed the second equation as well as the equation 1. So let's answer this question first, and then we'll see what the second equation gives us, even though the question isn't asking us. So the question asks for the acceleration. So what we should do is solve equation 1 for acceleration A and see what we get. I get acceleration is equal to F plus F cosine theta divided by M. And if you plug in the numbers given in this problem, you will get 5.9 meters per second squared. The unit of Newton divided by kilogram gives you meters per second squared back. So that's the answer, and we are actually done there. For the purpose of this question, you don't need to bother with the y-axis, but let me finish this up so that I can say one thing I want you to say. So solving the second equation for the normal force N, this is what you get. N is equal to mg plus F sine theta. And this is what I want you to point out. Sometimes in this class, people get into a habit of saying that normal force is equal to mg, because that is true in a lot of the cases. But I want you to realize that that is not the general rule. The general rule for normal force is normal force enforces acceleration parallel to the surface by not allowing the object to dig into the surface. So if in order to satisfy that condition, if the normal force needs to be greater than mg, or sometimes smaller than mg, then that's what it will be. So you can plug in the numbers here to find the normal force, but since it didn't ask, let's not. Alright, let's look at this example of applying the standard strategy. As a reminder, the steps in standard strategy are: draw the free body diagram, define the coordinate axis, break forces into components along these axes, and finally, this is what all these steps are leading up to: write down Newton's second law equations. Alright, let's look at the question. It says one end of length of a rope is tied to a tree. The other end is tied to a car stuck in the mud. The motorist pulls sideways on the midpoint of the rope, displacing it a distance of 2 meters. Assume the car slides slightly, but then becomes stuck again. If he exerts a force of some amount of newtons under these conditions, determine the force exerted on the car. Alright, it sounds like I should draw a figure. So let me start by drawing the tree and the car, and I guess they're connected by a rope, but it's not going to be in a straight line because it gets displaced at the midpoint. So let me draw this displaced midpoint of the rope, and this is the rope. I should have some length labels here. So the length of this portion of the rope is half of the whole length of the rope. And I'm going to give this portion of the length a label delta x. In this question, this would be 2 meters. Alright, the question says determine the force exerted on the car. So I guess it's asking for tension force exerted on the car. Alright, so I guess here there is a pre-standard strategy. By pre, I mean we need to draw free body diagram, which means we are drawing a diagram of forces acting on something. So the question is, what is that something? I hope after a short bit of thinking, you see that it's not the force on the car that we want to diagram, because if we knew that, then we would know the answer already. So that's not what we are ready to draw quite yet. We are looking for the tension. And I hope you remember from your reading or somewhere that you know some properties of tension, that if there's a tension pulling on the car this way, then this is kind of everywhere on the rope. So if I look at this portion of the rope, then there's tension pulling it down this way. There's on that portion, there's tension pulling it down this way, and this same tension is pulling on the tree this way. There's all these tension forces that you can take any one particular point on the rope, and it's being pulled apart. That's what tension does in both directions along the rope. So I hope all of that sounds familiar, which means if we can find the tension along any point on the rope, then we'll have our answer. So in the question, we are given how much force we apply on this portion of the rope. So that makes me think I can draw a free body diagram of this point here, and that'll get me to figuring out what the tension forces are. So let's draw the free body diagram of this point on the rope. I mean, I kind of just did there, but let me draw a bigger version. So this is a standard strategy step number 1, drawing free body diagram. And I'm drawing free body diagram of that point on the rope. Good thing I'm already representing objects by point. So there's the applied force F drawn in the vertical direction in the way we are drawing it right now. And we have the tension force. It's being applied at an angle. So I better label it on my diagram up there, and I will use the same label for the free body diagram. So the angle I feel is easiest to express is this one here. Let me call that theta. And if you find that same theta on the free body diagram, you'll find them here and here. And staring at this geometry for a while, I hope you can figure out what expression theta has. So we have this L over 2, we have this delta x, so theta should be arc sine of delta x over L over 2. That's why I was labeling those lengths. Alright, good. The next step is to define the coordinate axis. And this is where I said we normally pick it along the direction of acceleration. And here it says becomes stuck again, which means as the driver is applying a force, nothing is moving. So I think the acceleration is 0. So what do you do in those cases? So it's actually even better. When acceleration is 0, you have complete freedom to choose whatever coordinate axis you want. Normally, you should use this freedom to minimize the number of forces that you have to decompose into components. So let me choose my axis so that the y-axis is along the applied force F. That way, I don't have to decompose F. And it looks like even though I have two tension forces, if I decompose one of them, then the other one will look exactly the same. Alright, so next step. I had to break forces into components. So the only force I need to worry about right now is the tension force. There's technically two of them, but let me just do one as an example. So the tension can be broken into y component and the x component. And this angle here is the same angle as that theta. So the y component should look like t sine theta because it's opposite to that angle. And the x component looks like t cosine theta because it's adjacent to that angle. Good. Alright, now we are ready. We should write down the Newton's second law equations. That is, net force is equal to mass times acceleration. And you might be wondering, what mass? We are drawing a little segment of the rope. But not to worry, the acceleration is 0. So either way, it's going to be 0 anyway. So that makes our job easier. And in this case, let me cut out on some unnecessary work. And I won't even write down any equations along the x-axis because I can see from this diagram that x component of one tension force will cancel out the x component of the other tension force. Doesn't give me any information. So I'll focus on what happens with y components of the forces. So writing out that y component forces, net force in the y direction, or F, the applied force, minus, and remember there are those two tension forces, 2 times t sine theta is equal to 0. And that is the end of the standard strategy. We have one equation and one unknown. So great, I think we can solve it pretty easily. Let's go ahead and do that. Solving that expression for tension force, I get T is equal to the applied force F divided by 2 sine theta. So I hope you see that if the sine theta is a small value, then the tension is going to be a bigger value compared to this applied force F. And that's actually one of the reasons I like this example. It's one of the early examples of what we call simple machine, where you gain a force multiplier. You apply some amount of force F, and the force output that you get is greater than the force that you put in by some arrangement of things. So let me, I guess, first work out the angle theta. I think that'll give you some idea of what kind of multiplier we get. So looking at this information here, I guess we can work out the sine theta directly without putting it through any trig functions. Because looking at that expression, we should have sine theta is equal to delta x over L over 2 or 2 delta x over L. And we are given those numbers, 2 times 2 meters divided by L, 36 meters, or 4 divided by 36, or 1 over 9. Plugging that in, we get tension is the applied force divided by 2 over 9. So we are going to get a force multiplier of almost a factor of 4. Or, actually plugging in numbers, 517.5 newtons. It's quite a bit greater than the applied force. And this is a simple machine, similar to a mechanical lever that you might have seen in other contexts earlier. So this problem is also kind of an example of a type of question that you will see more later in the class. It's called static equilibrium. And a key condition in static equilibrium is that the acceleration is 0. And you will see some Newton's law problems like that right now in the next couple weeks. And a little bit later in the semester, after we do rotations, we'll look at more situations where there's one additional condition that gets brought in. These static equilibrium problems are important for two reasons. One, they are very practical. This is the type of thing that you would see often in engineering contexts. Two, the fact that acceleration is 0 makes it easier to have more complicated situations that are still solvable. So it ends up giving you more geometry practice. So it's good to have that practice. Here's one more example of standard strategy problems. As a reminder, these are the 4 steps to the standard strategy. First, you draw the free body diagram, and you define the coordinate axis along the direction of acceleration. And you use those axes to break forces into components. And all these steps will have resulted in a diagram that will allow you to write down Newton's second law equations. Alright, let's look at the question. It says a mass of fuzzy dice is attached to rear view mirror by a short string. The car accelerates at a constant rate and the dice hangs at some small angle from the vertical because of the car's acceleration. What is the magnitude of the acceleration of the car? Alright, looks like I should draw a diagram once again to help me think through this question. So let me start by drawing the car. This is the rear view mirror that the dice will be hanging from. And it says dice hangs at some angle. And all this is happening while the car is accelerating forward. Alright, I want you to pause for a bit and make sure that this picture makes sense. Imagine you are driving. You are accelerating as you are, I guess, starting from rest or whatever. Imagine something is hanging in your car. Do you expect it to hang back the way I've drawn it here? Or do you expect it to hang forward? Make sure you think that through. It is important. So once you have convinced yourself that whatever is hanging in the car will hang backward as the car accelerates forward, then great. Then this is the correct picture to start with. And we are now ready to start following the standard strategy steps. So we have to draw the free body diagram, and it's clear what object we are drawing free body diagram of, the dice that's hanging from the string. So let's draw that. This dot represents the dice, and it's hanging from the string, so there's a tension acting on that dice along the direction of the string. Oh, that means this is the angle theta. And as drawn here, the diagram is incomplete because it would have the dice accelerating upward diagonally this way, and that doesn't look right. So hopefully after staring at it for a while, I hope you realize there must be gravity. So gravity is pulling it down with the force of mg. But the way gravity is drawn, there's no way the dice can stay in the same position. There's going to be a net force. So this is the question you have to resolve. Is the dice accelerating? This is why I like this question. It forces you to rethink how you might have been thinking about questions like this. From your perspective, in the car, it's easy for you to look at the dice and think of it as being at rest, not accelerating. But as you think through this situation, what you have to realize is that everything in this picture is accelerating with the same acceleration as the car. So the dice is accelerating. It is accelerating to the right with the acceleration a. So this free body diagram is exactly what we expect to see. In the vertical direction, the forces will balance out, but in the horizontal direction, there will be a net force to the right. Okay, so let's move on to the next step, define axis. We figured out the direction of acceleration, so the axis should be along the direction of acceleration. Let's make this the x-axis, and this will be the y-axis. Alright, that looks good so far. Now it's time to break forces into components. The gravity is already along the y-axis, so we need to break down tension into x and y components. So we already have the angle labeled as theta, so the x component is opposite to that angle, so it should be t sine theta. So this is the situation I've been warning about, that even though it's the x component of the force, it is associated with the sine theta. Get into the habit of always drawing the triangle, then you will always get it right. Okay, so the y component is t cosine theta since it's adjacent to the angle. Alright, so we're done with step number 3. Now we are ready to write down Newton's second law equations. Net force is equal to mass times acceleration. And a reminder, this stands for actually two equations. Net force along the x direction is equal to mass times x component of acceleration, and the net force along the y direction is equal to mass times acceleration along the y direction. And here, because of how we did step number 2, the y component of acceleration is 0 by design, and that'll make some of our equations simpler. Okay, so let's go ahead and write them down. Let's do the x direction first. So the net force along the x direction are, I have only one force, the x component of tension. So t, not cos, sine theta is equal to mass times acceleration, and this is the whole acceleration since the entire acceleration is along the x direction. And if you are thinking of previous questions where we only needed the information from one component, you might be tempted to skip out on the y component. But I hope you look at the equation and realize that you have two unknowns. So this will be an example of a situation where you do need both components. Even though the y component cancels out to 0, apparently there's some information that we need to get from that. So the y component of the forces, net force in the y direction, is equal to, I have two forces, the y component of the tension force, T cosine theta, that's upward, call that positive, minus mg, gravity, is equal to 0. So this is the end of the standard strategy. It's a good point to stop, count the number of equations, and count the number of unknowns, and make sure that this is solvable. So the second equation didn't introduce any new unknowns. It just gave me tension again. So this is why we need the second equation in order to be able to solve for tension and then plug it into equation 1. So let's do that. From equation 2, I'm solving for tension, and we get tension is equal to mg divided by cosine theta. Alright, we are using the substitution technique. So let's call this equation 3, and we are going to plug this into equation 1. And this yields mg over cosine theta times sine theta is equal to ma. Oh, mass cancels out. So I guess we didn't need to know the mass of the dice, which is good because I was a little bit unsure how this mass applied to the pair of dice. It's a mass of individual die but well, it doesn't matter. So we can simplify sine theta over cosine theta as tangent theta. And with that little bit of simplification, we get acceleration is equal to g tangent theta. Or plug in the numbers. Let me use g is equal to 9.8. I get 0.44 meters per second squared. 0.44. Alright, that's it. So this is a challenging question, especially the first time you see it, because there are several steps which break you out of what might be called the normal way of thinking. But once you are trained in how to apply the standard strategy, this question is actually a lot simpler than the other questions you have seen. There are fewer forces and math isn't that hard. The difficult part is the initial setup and thinking through all the steps, and most importantly, avoiding all the pitfalls that could befall you if you don't carefully think it through. Okay, it says at a post office, a parcel that is mass slides down a ramp inclined at some angle from the horizontal, and it gives a coefficient of kinetic friction. All right, so that's a hint that we should be ready to use friction. All right, so I guess let's jump right in. The important part of the description here is that there is a ramp that's at an angle. Call that theta. Right now I'm not drawing a free body diagram. I'm just drawing a diagram. I like to visualize it, make sure I'm not missing anything. So I have a parcel box that is amount of mass that's going to be sliding down. All right, and I given the angle, and it tells me about friction, and it gave me a coefficient of friction mu, so I'll be using that. All right, that seems like that's all the information. So let's start. The first step is drawing the free body diagram. So here, it's kind of clear what free body diagram you're drawing. You're drawing free body diagram of the mass m. So once again, this is the step where you should be putting most thought into. You should be really being most careful not to have missed anything, to have thought of everything, to have done that. So, so as you are feeling like you haven't forgotten anything, let me start. So, so I like to draw forces in as they are needed. That helps me not draw unnecessary forces. And by continuing to ask, did I draw all the forces? I can convince myself that I didn't forget anything. So the first thing I need is gravity. There's always gravity, unless there's always gravity. There's almost never a situation where there is gravity. So I drew gravity. Then I ask myself, do I have all the forces or do I need additional forces? So I know the direction of acceleration, kinda, and this direction of force is not, this direction of net force is not consistent with the direction of acceleration. So there should be additional forces. Well, I need a normal force that's going to be in this direction, kinda. All right, that can give me acceleration that's kind of going this way. So that's looking okay so far. But I still ask myself the question, did I draw all the forces? And that's why I noted that there's friction here. This time I have to remember to draw friction force. So friction is going to be opposing the direction of motion. We know it's sliding down, so friction force must be going this way. Because it's tangent to the surface, it'll be perpendicular to the normal force, almost by design. All right, then that looks like that's all the forces I have. And so I ask myself the question, did I draw all the forces? And I included friction. Looks like everything's there. Good. Now I'm done with the step number 1. Then the rest of the steps are quite a bit mechanical. We define coordinate axis along the direction of acceleration. That makes things easier in step number 4. So let me define my axis this way. That's y is along the n direction, and this is my x. All right, so that's my axis, and it's defined in a way so that it's going along the direction of acceleration. Then step number 3, break up forces into components. So this axis also happens to be nice with step number 3 because the normal force and friction are already along the direction of y and x axis. So the only force I need to worry about breaking up into components is the gravity. And this is the part that takes a little bit of work of geometry, because the angle that you're given here is this angle here, theta. And after staring at it for a while, you might be able to locate the theta here. And this is the step I would go through. I would start by recognizing that this angle here is part of this triangle here, which would be a right triangle, which makes this angle 90 degrees minus theta. But this angle is part of this right triangle here. So that makes this angle here 90 degrees minus theta, and that works out to be theta. You see this situation quite a bit, so I hope it doesn't take you too long before you are able to locate this angle theta pretty quickly from the given angle theta here. So once you have located theta, then you are ready to write down the components. The opposite side has the magnet or length mg sine theta, and the adjacent side has the length mg cosine theta. So, all right. With that I have all the information necessary to do step number 4 without really too much thinking. All I'm doing at this point with step number 4 is just copying the information that already exists in the diagram into equation. So once again, I'm writing down the Newton's second law equation, net force along the x direction, and the net force along the y direction. Net force along the x direction. All right, let's see which forces are along the x direction. This time it's a little more interesting. I have mg sine theta, the component of gravity along the x direction, and I have friction. So let's write that down. So setting the sliding down direction as positive, I have mg sine theta minus friction force is equal to mass times acceleration. The block, the parcel is accelerating in that direction. And along the y direction, we have two forces, the normal force and mg cosine theta. I hope you know this is something that's interesting, and minus mg cosine theta. The first is that normal force is not going to be mg. It's going to be a fraction of mg because these two will be adding up to 0. And the second thing is, so I think if we were doing this question in the frictionless version, this y component is something that you might have just ignored, calling is something uninteresting, and that was true before you had the friction. Once you have friction, then you kind of need the normal force. So now we won't be ignoring this. We'll be working through here. So this is the kind of end of the standard strategy. This is where you should stop and check if you have the same number of equations as unknowns. So let's count our unknowns. We have m known, g known, theta known, friction force. I don't see friction force given in newtons, so this is not known. Acceleration, we are looking for it, so that's of course not known. Okay, all right. One equation, two unknowns, that doesn't look good. Let's look at the second equation. I have normal force. It's technically not known until we solve for it. Minus mg cosine theta. So I have three unknowns and only two equations. And that means I don't have enough information. And hopefully it doesn't take you too long of a staring to see that I am given coefficient of kinetic friction, and how am I using that information? And as you're thinking about it, and maybe even looking it up in the textbook, you should find this formula for kinetic friction. Kinetic friction is equal to normal force, is equal to, it's usually written coefficient first, coefficient of friction times the normal force. One thing to be careful here, when you are dealing with a static friction, it gets a little bit more complicated. But this is kinetic, so it's easier. So that's my third equation. And I think I'm done here because this third equation didn't introduce any unknowns, or introduce any new unknowns. So I have three equations and three unknowns. This is solvable. So let's solve it. That's, I guess, kind of what we are doing. So you can go any number of ways. Just the one thing to watch out for here, because the question is asking for acceleration. Acceleration is the quantity you want, which means you leave it to the very end to solve. You don't solve for acceleration right now, because right now you don't have tools to solve for acceleration. So, all right, so with that in mind, I do have one unknown already solved for in terms of other quantities. So let me just plug that in and see what I get. So from 1 and 3, I get mg sine theta minus f, which is mu n. Oh, I guess the first one I didn't write fk, but we understood it was the same friction force, is equal to mass times acceleration. All right, so we have one equation, two unknowns, so we still have some way to go. Fortunately, equation 2 has the normal force. in terms of other things, I think they are all known. So let me solve that for normal force. When I solve that for normal force, I get normal force is equal to mg cosine theta. Now I can use a substitution again, plug this into this equation here. Then I get mg sine theta minus mu. Don't forget that. Mg cosine theta is equal to mass times acceleration. All right. Oh, so even though the question gave us the mass of the box, I guess we didn't need it. So let me just cancel that all out of all three equations. Once I do that, I guess it is solved for acceleration already. So let me just write that down. The right-hand side, acceleration first. Acceleration is equal to, and if I want, I can actually factor out g. So let me do that. G times, and now I have this numerical parameter, sine theta minus mu cosine theta. All right, I think that's it. From this point on, it's a matter of plugging in the given numerical values of theta and of coefficient of friction 0.03. All right, I guess part B, let me just leave that for you. As the hint says, this is just a kinematics question. Once you find the acceleration in part A and you confirm with my open math that is correct, then you should be able to, I guess, so I have acceleration and displacement. I think I can use a V squared formula. So I'll have you use V squared formula to do that. So okay, let me do this question. So even before I read the question, because of the chapter it's in, I know we are going to be using standard strategy. So let me write down the steps of standard strategy to refer to as we are going through this problem. So the steps of standard strategy are, first, we need to draw free body diagram. And this is the step that should take you the most time and care, because this is the step where it's easy to forget some things. And oftentimes, if you forgot something important, then it kind of doesn't matter how well you do the remainder of the steps. Your final answer will likely be wrong. So please make sure when you draw free body diagrams that you pay attention and do it carefully. Don't miss any forces and don't identify any forces that are not actually there. So once you've drawn free body diagram, then you need to define coordinate axis. And when you define coordinate axis, the main thing that you're looking for is what is the direction of your acceleration. And it usually works out best if you make your positive x-axis parallel to the direction of expected acceleration. Once you have that, then on some problems you will have to break down forces into components. In this problem, I don't think I'll end up doing that, but let me write it down as a step. And the final step, which will set you up for the rest of the problem solving, is writing down Newton's second law equation. So write down acceleration is equal to net force divided by mass. You might have seen it written the other way around. Net force is equal to mass times acceleration. This form makes the causality clearer, that it's the net force causing acceleration, not the other way around. So that's the steps of the standard strategy. So we will just go through it one at a time. So we'll start out with the free body diagrams. Now I see that in this problem of let me read the question and see what it is we're being asked for. It says, as shown, the coefficient of kinetic friction between the surface and the larger block. Okay, so there's some kind of a coefficient kinetic friction here. I'm using 2 for this. So this is going to be my mu2. And the coefficient of kinetic friction between the surface. Okay, so I'm dealing with the friction, two different coefficients that I better track. So we are given the force is some number of newtons, and the mass, I guess, so we are given basically masses of both object because this is not the second mass, it's twice the mass. So m is that. What is the tension? Okay, so there's a tension force here that I'll need to uh, I'll need to be looking for. What is the tension in the connecting string? Okay, that sounds good. I doodled while we were reading the question to make sure that I understood the question, that I didn't miss anything. And I guess in this question, the important thing not to miss is the fact that the coefficient of kinetic friction is different for the two blocks. So, okay, let me draw a free body diagram. I'll just draw one at a time. And by the way, I see this often where people try to draw forces on this diagram itself, and I don't recommend doing that. No, I might not always deduct a point when I see people doing that, but so the purpose of a free body diagram is to illustrate forces clearly. You really don't want anything else on your free body diagram that's not force that could confuse things. That's why I like to represent the objects with a single dot and use this dot as a point to anchor all my forces. And when I draw forces, it will look like forces are coming from the dot. And when you're drawing free body diagrams, you're drawing forces on the object. So like there shouldn't be any need to draw forces like this. The way we draw the forces as coming from the dot is because when you draw it that way, it's easier to draw other auxiliary figures or do things. It's just the diagram is a lot cleaner when you do it that way. So I'm gonna need the forces for block M, and I'm going to need the forces for block 2M. Make sure you are drawing separate diagrams for each of your objects. So I need to stare at this for a while, think through, make sure I include all the forces. As you're drawing forces, a good things to remember to draw are the forces that your problem gives you. Problem tells you there's a force F on mass M. All right, let's draw that. There's a force of magnitude F acting rightward on mass M. All right, I'm gonna have that. And the other, so any explicitly specified forces. And other forces that are good to draw are gravity. Hopefully, once you've done gravity, then it will give you inspiration for other forces that should be there. So let me draw gravity for both of the objects. I have gravity pulling this mass down, mg, and also gravity pulling this mass down, 2mg. And as you're completing your free body diagram, the question you should ask yourself is, um, have I drawn all the forces? And by that I mean, from the question description, you have an intuitive sense of the direction of acceleration, in what direction your object should be moving. That acceleration should be rightward. So when you've drawn all the forces you have drawn should match that sense of acceleration you have for both blocks. Now, in the diagram I have so far, I have acceleration going like this and acceleration going like this. Okay, those are obviously not right. So I need something to counter that gravity. So I need a normal force. Um, so that's where this understanding that it's touching a surface and there should be contact force from the surface is useful. So let me draw a normal force. I have a sense there'll be different normal forces, so let me label this N1 and label this N2. Okay, so block M looks okay. It looks like we can get a rightward acceleration. Um, um, uh, so you might be justified in thinking this free body diagram is complete. It's not. We have two more forces I need to include, but we'll get there. Now, as you look at mass 2m, it's clearly missing some forces because we do have an innate sense that it should be accelerating to the right, and I need rightward force to get rightward acceleration. So this is where you look at the setup, think about what can provide that rightward force, and this is where the hint I give you about the types of force is useful. The only single non-contact force in this class is gravity. So all forces other than gravity, you should be able to identify something that's touching the object. So you look for the things that could be touching this block and applying rightward force. Oh, there it is. There's the string touching this block and probably pulling it rightward. So I need to draw that force. I need rightward, the force of tension on mass 2m to give it rightward acceleration. Okay, now before you call it done, there's a check that I'd like you to get into habit of doing. I call it Newton's third law check. It's a check that you need to do whenever you are drawing free body diagrams for a system with two or more objects. It amounts to a check of, is this an internal force or external force? If it's an external force, great, you're done. Nothing else to worry about. If it's not an external force, if it's an internal force, then you need to identify the action-reaction force pairs. That's what Newton's third law says we need to have. So whatever free body diagrams we draw should be consistent with that. So let me go through just each of the forces to go through for that check. The gravity, they are both external forces. They come from Earth. Earth is not part of our system. So there's going to be reaction force on Earth, but we are not drawing those. We're fine. Same thing with the normal force. They're not coming from Earth. They're coming from the table, but the table is not part of our system. We're not drawing any forces there, so we are fine. Apply the force. It's probably being applied by like a person who's not part of our system, so that's also external. Now, when you look at this tension force, this is where you have to be a little bit careful. You might be thinking, "Oh, tension force, it's coming from this string, which is not part of our system." So you might be thinking it's external force, but keep following the string and notice that the string is also attached to here. Um, so it's not always, but in arrangements like this, you might find that tension force kind of acts like a mediator between two blocks. So in this case of tension force, I would treat it as an internal force. This tension force is being exerted through the string by this block M. So I need to have the reaction force on block M. It's equal in magnitude, so that's why I'm going to use the same letter for both of them, and it's opposite in direction, as Newton's third law says. In such situations where you have pulleys and other things that could redirect the tension force, the way you approach it might be a little bit different, but just watch out for that. That when you identify tension force on one object, you also have to remember there might be tension force on other objects. Here, I would describe this kind of like Newton's third law pair. And it's at this point, it is easy to forget some information given in the question, which is why I always, take the time to diagram stuff as I, go through the question. And I notice that I haven't used this information. They gave us a coefficient of kinetic friction, and when you look at my free body diagram, I haven't drawn any friction force because I'm so used to trying to ignore friction force. Now, when a question explicitly tells you about friction force, then you can't ignore them anymore. You have to account for them. So let me account for them. So for this block, so they are all going to be moving to the right, so friction force should be leftward to kind of reduce the sliding. So let me draw a leftward friction force 1, and I'll be using that later to actually work out what that is. And on block 2M, there will also be leftward friction force 2. So, all right, now we ask the question again. Did we draw all the forces? And hopefully at this point you can say yes. Both the blocks, from our intuition, we think they should be accelerating to the right, and we've drawn enough forces to make that happen. And for every single thing that's touching the blocks somehow, we've accounted for some form of force that we anticipate being there. So we're done. Good. That was I think 10 minutes. But as I was saying, drawing free body diagram, that's the step where it takes the most care. Once you've done that step correctly, then the rest is almost automatic, mechanical. You should be able to do it in your sleep. So let me do that. Not sleep, but just do it. So step number two, we need to define our axis. So I'm gonna just use simple axis of rightward being positive x and upward being y, so that x is along the acceleration. And I think for this question I can use the same axis for both blocks. They don't have to be, but here same axis makes sense for both. I've done that. The third step is break forces into components. Here, all the forces are either horizontal or vertical. So there's nothing to break into components. So I'm done. And finally, we need to write down Newton's second law equations. And if you've done steps 1 through 3 well and correctly, then step number 4 is kind of a mechanical step where all you're doing is just copying down the information that you already have in this diagram. So as you're doing step number 4, all you should need to do is just copy that down in the form of mathematical equation. So let me do that. I know I'm gonna need minimum of 4 equations, or I'll start with the 4 equations. I need an equation for each object and for each dimension, each direction. So I have 2 objects, each of which have x and y direction. So 2 times 2, 4. That's how many equations I'll have. So, so yeah, let's just start out with the first equation. So, let me label them so I don't get them mixed up. So I'm gonna need the equation 1 for x direction, and also equation 1 for y direction, equation 2 for x direction, and equation 2 for y direction. So I'll say equation 1 for x direction. So it's going to result in some acceleration. I'll label it A is equal to the net force. So I'm looking at this diagram here. In the x direction, I have the applied force F, I have tension force T, and friction force. I'm going to write my equation so that the directions are indicated in the equation. So all my quantities should be positive. So that looks like F minus tension minus the friction force, that's the net force, that divided by the mass, that would be that big M there, that's equal to acceleration. Good, 1 down, 3 to go. In the y direction, it's no acceleration, 0. That's kind of how we set it up on purpose. We have 2 forces, and in other questions, we might have skipped it, saying, oh, nothing interesting happens in the y direction. In this question, I have a sense because we have friction, we'll have to worry about normal force, which we get from the y direction. So let me write it down. So we have normal force, upward normal force, minus gravity, mg. And that, let me just finish writing this. That divided by mass is equal to 0. I could kind of get rid of mass multiplying both sides by m. That's fine. Let's keep going. 2 more to go. So for mass 2m, let's write. So it's going to be accelerating to the right. And here, pause a little bit and convince yourself that both masses are accelerating with the same magnitude of acceleration, so that we can justify using the same letter for both of them. In cases where somehow that's not true, you have to use different letters. We have tension force pulling it to right. Minus the friction force, F2, that's the net force, divided by 2m, that's our acceleration for block 2m. And in the y direction, do the same thing, 0 is equal to n2 minus 2mg divided by 2m. Let's be careful here. Okay. So we got 4 equations. Let me count the number of unknowns to make sure that we have enough information by which I mean equations, to solve this system of equations. um, so acceleration, while they're not asking for it, I also don't know it. So this is an unknown one. Okay, apply the force, we are given that, so good. Don't need it. Tension, they're asking for it, so it's unknown. Friction force, we do have the coefficients, but not the force. So this is an unknown. Sorry, man, make me nervous. Mass, we know them. Normal force, okay. We're not given them, so that's another unknown. And one, mass known, okay. Tension, it's unknown, but I already counted it. No need to count it again. Friction force 2, that's an unknown. 5. And normal force 2, that's another unknown. 6. So we have 6 unknowns, 4 equations. So what that means is, so the following the standard strategy landed us here, and that's great deal of progress forward. And sometimes, if you're lucky, the equations that you have written down will be it. You have 4 equations, 4 unknowns. You go ahead and solve it. Questions like this one, you might have 4 equations and 6 unknowns. So you need to find 2 more equations. And those 2 more equations, they will come from using the given pieces of information, like a coefficient of kinetic friction. You hopefully remember the given coefficient of kinetic friction that you can say this about the friction force. So F1 should be the coefficient mu1 times the normal force that's associated with this surface, so N1. And it's encouraging in that when I look at this, my fifth equation, there's no additional unknown introduced here. All the F1 and 1, they were all counted before. And I can write the same thing for F2 is equal to mu2 times N2. That's my sixth equation. So I have 6 equations, 6 unknowns. I should be able to solve for it. Let's solve for it. Oh, so I could solve for it by hand, but I feel like this is a good opportunity to demonstrate the tool that I really want you to think about using and get good at using, which is Sage Math. So Sage Math is super efficient in solving simple system of equations like this. Simple in that they don't involve trig functions um, and at the same time, doing this by hand, it's tedious. So let me launch Sage Math and just do this on Sage Math. I think that can help me save a little bit of time and also help demonstrate use of this great tool that I want you to use. Computer algebra system, professionals use it all the time in their work when they need to work out math. So um, it's a yeah. So and yeah. Sometimes I've seen where people struggle with algebra, especially later on when we get to static equilibrium, where you could have a lot of equations, each one of which is simple. And a tool like Sage Math can be something that helps you get through that hurdle. Like, in your other math classes, like if you have trouble multiplying 2 3-digit numbers, you don't let this stop you, you just use calculator. And this is like a calculator for symbolic computation. So I need to define my variable, so let me do that. Acceleration, tension, friction force 1, normal force 1, friction force 2, normal force 2, and I think I forgot something. 1, 2, 3, 4, 5, 6. Oh, okay, that's it. So those are all my variables. Oh, but I also need to define my known quantities. I'll plug in numbers for them later, but I need the F for force F, M for meson, reference meson, and G for gravitational acceleration. I think that's it. If I miss something, it will complain later. So I need to define my equation. So let me just write down my equations. Equation 1, that's my acceleration, is equal to, there's a difference between this single equal sign and double equal sign. This is an assignment symbol. This is the equality symbol. That's F minus T minus F1 divided by M. And just to make sure I typed it correctly. And I'll type in the remainder of the equation without talking so much. mostly in the interest of time. And you have to make sure you always put in this multiplication symbol. Sage Math doesn't understand implied multiplication. It's a contrast with your my open math, which does understand implied multiplication. Oh, I didn't define mu. Okay, I need to define those. Mu1 and mu2. Okay. Okay, let's just put them into an array. Equation 1, equation 2, equation 3, equation 4, equation 5, equation 6, and make sure I wrote them down correctly. They look correctish. Correct enough. So in Sage Math, there's a function called solve. Oh, let me just bring up the help for solve so that you can see um, the kind of documentation that's available within Sage Math. This is one of the reasons I recommend using this interactive version and not the. I mean, there's an online Sage Math cell that you can use without installing anything on your computer. The downside is that it's harder to use those to look up this documentation. I mean, you can, but it's harder, more cumbersome. So it's an example like this. That's what I'll follow. So this syntax is exactly what I want. I'll have it solved for all the quantities, and I'm just gonna need the tension from that. So okay, so I'm gonna have it solve my equations for the unknowns that we have identified. For let me put tension first, so that it will come first. The rest of the variables I don't really care, but I still kind of need to specify them so that I'm telling Sage Math that these are my unknowns, and the rest are known quantities. So um, Sage Math will treat like F and M and the mu ones and two, mu one and two as known quantities, and just solve for these in terms of those known quantities. So it'll do that in a bit. Sometimes computer algebra system will complain that it, that it doesn't know if I don't know if m is positive. Computer algebra systems tend to deal with these in a very general way. So for more complicated equations involving square roots and whatnot, it might complain that there's a syntax you can use to tell Sage Math what to assume. So okay, so it solved everything, and really all I need is really this first element. So let me get at that. That's the first element, which is the first set of solution, the only set of solution, and the first element of that. So I think that will give me that. Yeah. So let me plug in the numbers that they give us. So this there's a syntax for it. It's the substitution syntax. Let me make sure. Yeah, and you can substitute with something like this. You say F is equal to 13 newtons, and I'm just gonna do everything in basic SI units. That'll make all the units work out right. My M is equal to 0.8 kilogram. My mu1 is equal to, I labeled it there, that's why I labeled it, 0.29, and my u2 is 0.22, and my g is equal to 9.8 meter per second squared. I think that's all. Let's see what it gives us. Okay, yeah, 8.3 Newton. So let's plug in the number and see that it's correct. So yeah, this is a so the part of problem solving that can't be automated is all of this. This is what's important to learn because Sage Math can't set up these equations for you. You have to come up with the ultimate question for the machine to be able to answer. And once you have the set of equations, then getting an answer, it's just a matter of learning a relatively simple programming language.